Hey everyone, thank you for joining us again for our virtual TAP Talks. So this event is particularly special because we're going to talk about the recent Nobel Prize that was just won, which is, I believe it was the 4th Physics Nobel Prize won by a female. She shared it with 2 other people, but I just thought that was a fun little fact to toss in there. We have 3 experts who work with black holes, and they will be each giving a short talk telling you about the things that they particularly work on and information for the black holes. So the 3 speakers we have today are Dr. Mike Kesden from the University of Texas in Dallas. We have Dr. Weinberg from the University of Texas at Arlington, and Dr. Cendes from Harvard University. And so without further ado, Michael, if you don't mind, you are welcome to share your screen and let's get started.
Sure. Thank you very much, Leslie.
Watching live, please put all your comments and questions on the right-hand side in the chat, and I will ask the questions after the talk. That way we can get them all together and just stay kind of organized. So please put all your questions, we'll collect them all and ask them.
Thank you very much, Leslie. It's a real pleasure to be here and to talk about the most recent Nobel Prize in Physics. As we've heard, I'm Dr. Mike Kesden. I'm an associate professor of physics at UT Dallas. And we've decided to conduct this talk like a relay race. I'm going to be giving the first leg of the race. Nevin's going to take over in about 15 minutes. And then Yvette is going to bring us over the finish line. And so the title of our combined talk is Massive Black Holes Lurking Throughout Our Universe, and in particular focusing on this most recent Nobel Prize in Physics. So this is, these are photographs of the 3 most recent Nobel laureates, along with the actual citation issued by the Nobel Prize Committee. The Nobel Prize can be shared by at most 3 different individuals. They have to be alive presently. And the way that when they split it among 3, they actually split 1/2 goes to one of the people, and then the other half is split by the other 2 people. So the 2020 Nobel Prize in Physics was awarded jointly, with half of the prize going to Professor Roger Penrose of the University of Oxford. And the citation on his award is for the discovery that black hole formation is a robust prediction of the general theory of relativity. And the other half of the prize was split equally between Dr. Reinhard Genzel at the Max Planck Institute in Germany and Dr. Andrea Ghez at the University of California, Los Angeles. And theirs was for the discovery of a supermassive compact object at the center of our galaxy. And so in keeping with our relay portion of the talk, I'm going to be focusing on Dr. Penrose's half of the prize, which was primarily for theoretical results. He's the theorist. And then Nevin and Yvette will be talking about the other half of the prize and the observational side of looking for black holes. So the story of black holes actually goes back a lot further than one might think. This is a portrait here of the Reverend John Mitchell, who is a member of the Royal Society in the United Kingdom. And he was the first person to predict, he didn't use the phrase black holes, but the first person to predict the existence of dark stars in a paper that he wrote in 1784. This is an actual quote from that actual paper, over 200 years ago. I like to kind of quote from these because it's just amazing to me to, get such a connection to the scientists of the past. And so the language is a little stilted, but it's still very clear to us today. He says, if there should really exist in nature any bodies whose density is less than that of the sun, and whose diameters are more than 500, not less than that of the sun, and whose diameters are more than 500 times the diameter of the sun, since their light could not arrive at us, the existence of bodies, under these circumstances, we would have no information from light. And so where did that come from? What does that mean when he came up with that number? So he obviously 1784 was a little bit past Isaac Newton's time, but he was a contemporary in that century. He knew nothing about relativity, but they knew about Einstein. They knew about Isaac Newton's theory of gravity. And in Isaac Newton's theory of gravity, there's a concept called the escape velocity. That if you're on the surface of an object and you throw something, if you throw it above some certain speed, then rather than falling back down, it will keep going forever and out to infinity. And so in Newtonian gravity, you can calculate that escape velocity. It just depends on the Newton's constant for the strength of gravity, the mass of the object, and the radius of the object. And here I've just done a little bit of algebra. I put in the volume of the mass times the volume times the density. That's the mass of the sphere. And then I've just done a little bit of algebra to solve for r. And what I find is that if the density of the object is the density of the sun, which is about 1.4 grams per cubic centimeter, it's about 40% more dense than the beverages we're drinking now, then the radius of that object is about 400 times the radius of the sun, and that's where this 500 comes from. And he said that this came from saying if we set the escape velocity of such an object equal to the speed of light c, then nothing, even light thrown from the surface of that object, would fall back down. It couldn't get to observers far away. And that's what he meant by saying we could have no information from light. So these things, if no light could escape such objects, they would appear as dark. And so he hypothesized the existence of such dark stars. And if in this algebra you instead solve for the mass of such object, you get about 10 to the 8 solar masses. 10 to the 8 is scientific notation. That stands for 100 million. And a solar mass is the mass of our sun, which is about 2 times 10 to the 33 grams. So we're talking about something 100 million times more massive than our sun. So back in 1784, John Mitchell was predicting that we could have these dark stars. And then he also said, though, if, even though these stars were dark, any other luminous bodies should happen to revolve about them, we might still perhaps, from the motion of these revolving bodies, infer the existence of the central ones with some degree of probability. So this idea that even if the central object itself was dark, if there were luminous bodies like stars orbiting that dark object, we could observe the motion of those stars and infer the presence of the supermassive compact object. And so it's just extraordinary to me that John Mitchell, 240 years ago, was making predictions that read like they could be written from the Nobel citation in 2020. So this was the story of black holes in Isaac Newton's day. Of course, our understanding of gravity was revolutionized by Albert Einstein, who came up with his theory of relativity in 1915. This is a young Albert Einstein on the left here. And he radically reinterpreted our understanding of gravity. Instead of the inverse square law force, where two massive objects experience gravitational forces inversely proportional to the square of their distance, his general relativity reinterprets gravity as an effect of space-time curvature, that he unified three-dimensional space and one-dimensional time into four-dimensional space-time, and the presence of mass could curve that space-time, and then objects would travel along curved paths as if there was a force acting on them. And only 3 short years after Einstein developed his theory of general relativity, Carl Schwarzschild in the center here found solutions to Einstein's equation, spherically symmetric solutions that we now interpret as black holes. So as almost over a century ago, there was the theoretical idea of black holes. And then another 45 years after that, Roy Kerr here on the right came up with a more general solution that rather than being a perfectly spherically symmetric, was axisymmetric about an axis. And that now corresponds to the rotating black holes that astrophysicists use to describe black holes today, that are parameterized by a mass and by a spin. And that spin is important because...
Dr. Kesden, can you tell us what the axisymmetric means? I think that might not be a normal vocab word.
So an axis, so I apologize. So an axis is just a line. And something that's symmetric means that if you rotate it about that axis, it remains the same. So something like a sphere is spherically symmetric. If you rotate it, a sphere looks like a sphere, whereas a can of soup, a cylinder, is axisymmetric. If you rotate it about an axis, perpendicular to the lids of the can, then it remains the same. Does that answer your question, Leslie?
That's perfect. Thank you so much.
Sure, no problem. And so these are the as of 1963, we've had these solutions to Einstein's equation describing black holes. So this is all theory so far. John Mitchell didn't see anything. None of these guys saw any black holes. But then starting in the 50s, we started the radio astronomy starting to come into its own. And Alan Sandage, as part of the third Cambridge survey, found a bunch of radio sources in the sky. Yvette's going to tell us more about that later. And the 273rd source in that survey we now recognize as the very first quasar. Quasar is an acronym for quasi-stellar radio source. So it means something that's quasi-stellar, very point-like, very compact, but it's a powerful radio source. And then a few years after that, Barton Schmidt and Bev Oak found an optical companion to that radio source and were able to tell that it was very far away from us and hence had to be incredibly powerful and very bright. And then Fred Hoyle and Willie Fowler, writing a theoretical paper hypothesizing about the nature of these strong radio sources, wrote here that they knew it was very bright, they knew it was varying very rapidly and had to be compact. And they said, we have no idea how to trigger such a thing unless the stars are packed so close together that they could form a single object. And that was the thing they were exploring in this paper. We find the concept of stellar-type objects with masses of up to 10 to the 8 solar masses very strange. Hold on, let me just tweak this. Teams is giving me a little headache. Here we go. The concept of stellar-type object with masses of 10 to the 8 solar masses is strange, but the very nature of the case demands an unusual physical situation. The point of view we wish to examine is the following, that at the centers of galaxies are star-like objects, very compact objects, with masses ranging from about 100,000 for a normal galaxy up to 100 million for abnormal galaxies. To the argument that such objects would be unstable and cannot exist, we turn a blind eye. So here they've said we see these extraordinarily powerful compact radio sources. The only thing we know that is compact is stars, but to be powerful enough, they'd have to be millions of times more massive than the sun. Theory told them that you couldn't have something that would be, a star couldn't be that massive and would be unstable, but they just ignored, they turned a blind eye to that problem. But Roger Penrose got the Nobel Prize for not turning a blind eye to that problem. And so 1964, just a year later, in this very famous paper he wrote, Gravitational Collapse and Space-Time Singularities, in Physical Review Letters, he completed this proof that, so here what we see on the right here, this is the only figure in this 3-page, it's a short paper, but it's a gem of a paper. And this is the only figure in that paper, and it's something called the space-time diagram. I mentioned earlier that Albert Einstein unified 3-dimensional space and 1-dimensional time into 4-dimensional space-time. It's hard to draw 4-dimensional pictures. So what people like Penrose do is they kind of suppress one of the spatial dimensions. So they consider 2 spatial dimensions, and then they have time in the 3rd dimension. So time is moving upwards in this picture. And here what he's showing is that if you've got some object, some matter, like one of those massive stars that Willie Fowler was hypothesizing about, it's going to collapse. Even Hoyle and Fowler realized it was unstable. And as it starts collapsing, it will eventually form this trapped surface, which we interpret as an event horizon. So what this is showing, these lines here, these little eyeballs here, this is us. We're an observer that's outside the black hole. And light, everything has to go forward in time, and it can also move in distance as well. And each of these little tiny cones here is showing that light, which is the fastest thing there is, has to move forward in time, and so it can only move outwards in the directions of these cones. But as this object gets more and more compact, these cones, rather than having the axis being vertical far away from the black hole, start to get tilted. And by the time they hit this cylinder, this event horizon, they're tilted such that the cone only opens inwards. Light cannot escape from outside this event horizon. And so even though this is in space-time, it's very different than Newtonian gravity. John Mitchell was right back in 1784. So objects that have event horizons are black holes. And what Roger Penrose got the Nobel Prize for was showing that whereas Schwarzschild and Kerr had very symmetric black holes, what Penrose shows that for any arbitrary lack of symmetry, it doesn't matter. That eventually, inevitably, all that matter would move forward in time and form this singularity, this point of infinite curvature at the center of the black hole. And so it was robust to being messy. And that robustness, black hole formation is a robust prediction of the general theory of relativity, as the Nobel Committee said. That is why he received the prize. And I just want to mention that, so this was a 1964 paper. The year earlier, Penrose attended the 1963 Dallas Conference on Gravitational Collapse, which was hosted by the precursor of UT Dallas. And so this idea of gravitational collapse, Dallas was kind of right in the heat of the action back then. I think I'm going a little over time here. But let me just mention before I hand the ball off to Nevin, that now, stepping away from history and going back to the present, we now think there are black holes lurking throughout the universe, as Leslie said. People have fears. You hear about a black hole, you watch, this was from the first remake of Star Trek with Chris Pine, and the Enterprise barely avoided the event horizon of a black hole. But we don't really have much to fear. Very far from a black hole, its gravity is no stronger than a normal object. It's only when you get near that event horizon that it's impossible to escape. And those event horizons are very tiny. If the sun collapsed into a black hole, its event horizon was only 3 kilometers. So the galaxy is very big. We're far from the black holes. There's nothing to fear. And in those solutions, the mass of the black hole is just a parameter. In theory, it can take any value. And that's what these kind of Russian nesting dolls are showing. We can have itty-bitty black holes and big massive black holes and anything in between. And so the ones we've found so far are stellar mass black holes. These form from the collapse of stars more massive than our sun, between about 5 and 100 times the mass of our sun. And supermassive black holes that Reinhard Genzel and Gez received their Nobel Prize for studying, which can be anywhere from 100,000 to 10 billion times the mass of the sun. And these reside at the center of galaxies. And there's an ongoing search for that missing link of intermediate mass black holes in between this range. And so if we want to learn more about black holes, and in particular, if we want to test whether Einstein was really right, we want to get data from as close to that event horizon as possible. And one of the things in terms of giving you the history and then giving you my own personal research interests, I work on gravitational waves as one of my key research interests. The 2017 Nobel Prize not too long ago was awarded to the Laser Interferometer Gravitational Wave Observatory, LIGO, for measuring gravitational waves from binary black holes. The big picture here is that you've got 2 black holes orbiting each other. They cause ripples in the fabric of space-time, which travel billions of light years to us here on Earth. This is showing the Hanford and Livingston facilities of LIGO, which basically look like 2 giant L-shaped detectors with arms that are 4 kilometers long. And there's laser beams bouncing back and forth on those arms. The gravitational waves stretch and squeeze space-time. The lasers fail to cancel out each other. Photons get into our photodetector, and we see indirectly the gravitational waves. And there's plans that these are sensitive to the stellar mass black holes. Those supermassive black holes that Genzel and Gez found are the subject of a future space-based mission, LISA. And so this is just a quick synopsis of the event, the very first gravitational wave discovery back in 2015. We've got 2 binary black holes. They spin around, they orbit each other, they emit gravitational waves, lose energy, get closer and closer together. Their separation, the distance between them is going down. As they orbit faster and faster, their speed's going up. And they get so close that they eventually merge, their event horizons touch, 2 black holes become 1, and then that final black hole rings down to a single black hole. This is that signature. And what's amazing is that by sheer coincidence, these gravitational waves are very different from sound waves. They're traveling at the speed of light, and they're traveling through vacuum, unlike sound. But by sheer coincidence, their frequencies are roughly the same as those heard by the human ear. So we can actually translate this waveform into sound and play it. My sound isn't working on Teams, but you'd hear a as the frequency gets higher and higher, the amplitude gets bigger and bigger, and so we can kind of listen to these black holes. Oh wait, do you hear it? No. So the Nobel Prize in 2017 was shared by Kip Thorne, Ray Weiss, and Barry Barish, who were the leaders of LIGO. This is showing the LIGO facility, the control center, an image of gravitational lensing by those binary black holes, and one of these amazing 60-kilogram crystal test masses in the LIGO detector. And so for my final slide, I'm going to say, where has LIGO left us in the past 5 years? That discovery was in 2015. Until its shutdown in March due to COVID, LIGO had seen a total of 66 gravitational wave candidates. We've now learned about black holes. Black holes are the end state of these stars, all the way from tiny black holes that maybe are only 2 or 3 times the mass of our sun, out to the biggest final black hole is about 160 times the mass of our sun. And in the future, in the next 5 years, we're going to have a detector in Europe, a detector in India, a detector in Japan, and then 10 years from now, next 3rd generation detectors in Europe and in the US. We may be finding 100,000 of these events every single year. And so it's the gravitational wave astronomy has been born, and we're going to go from the first discovery to seeing every single black hole merger in the entire universe in a 20-year span of our lifetimes. It's incredible. LIGO has taught us a lot about these stellar mass black holes at the bottom, at the center of the nesting doll. And now I'm going to hand things off to Yvette and Nevin, who are going to tell us about those bigger supermassive black hole cousins they have.
That's awesome. So before we move on, I would like to ask a couple of questions that are very pertinent to your talk, if you don't mind.
I don't mind at all.
Thanks. So one is, I'm going to paraphrase a little bit, but what happens if a gravity wave hits your brain?
What happens if a gravity wave hits your brain? Okay, so this is a great question. So remember I told you this is LIGO. This is the facility, one in Washington and one in Louisiana. And this tunnel here is 4 kilometers long. And do you know how this gravitational wave, it stretches and squeezes that tunnel, and the amount its length changes is 1/1000th the width of a proton. 10 to the minus 18 meters. This is the most sensitive measurement humans have ever done before. And so if a whole 4 kilometer tunnel is squeezed 1/1000th the width of a proton, imagine how the tiny distance that your little head would be squeezed. And so the short answer is it's utterly undetectable. The strength of these things is just nowhere. It's so hard to measure. It's no threat to people. If you were really right here at the black holes, you might get into trouble. I think Yvette's going to talk a little bit more about the tidal forces really in the vicinity of a black hole.
Okay, and then one more before we move on. We have more questions. I've got all of them. We will cover them at the end once we got through the talks and all 3 panelists can talk about it together. But lastly, because I think this is pretty important, could you explain what a singularity is?
That's a great question. Another great question. And I wish I knew the answer to that question. I've got a Nobel Prize myself. So theories, scientists, you always hear it's just a theory. Oh, what is science? It's just a theory. We see data and we come up with theories that fit the data. So part of the problem with understanding singularities is they're inside these event horizons. So because nothing can get out of the event horizon, we can't learn about the singularity. Nothing can get out. So it's very hard for scientists to test their theories when there's no data. And actually, another thing that Roger Penrose is very famous for was saying that there are no all the singularities in the universe live inside event horizons. He called that the cosmic censorship conjecture. There are no naked singularities. Formally, what it is that curvature. I said that if there was no gravity, that everything would be flat, geometry would be Euclidean. Gravity bends space. And so Euclidean geometry breaks down. What a singularity is a place where the space-time curvature goes to infinity. And so infinity is hard for us to deal with. Our theory breaks down. It's kind of a sign that Einstein's theory, as brilliant as Einstein was, the journey continues. And so we'll need a new theory of gravity to really explain what's going on there. His theory is breaking down there.
Awesome. Thank you so much. We will come back and ask more of your questions later, but before then, could we switch over to Nevin? And would you mind talking about your section, please?
Yes, sure. So let me share my screen. Let's see. Can you see that?
Yep.
Okay, great. So thanks, Mike, for the nice talk, and thank you, Leslie, for the invitation. So yes, I'm Nevin Weinberg. I'm an associate professor in the physics department at University of Texas at Arlington. And so I'm going to talk about the measurements of stellar motions in our galaxy, in the Milky Way galaxy, at the center of our galaxy, that show that at that location in the center is a supermassive black hole. And so let me start by just sort of orienting everyone to what our galaxy is and where we are in it. So our galaxy is a spiral galaxy, and we're about 2/3 of the way out from the center. And so that distance is about 26,000 light years. So a light year is how far a light will travel in a year. And just to give a sort of feel for what that distance is, the moon is about 1 light second from Earth. The sun is about 8 light minutes. So 26,000 light years is a pretty good distance. It's kind of local on a sort of cosmological scale where we have other galaxies that are billions of light years away, but it's still, a good ways away from us. And of course, this picture here on the left is not a picture of the Milky Way galaxy because we're inside of the Milky Way, and so we couldn't get a picture like this. But so this is some other galaxy, but we have an idea that it's probably looks something like that. And so if you want to know where the center of our Milky Way is, you just have to look in the direction of the constellation Sagittarius. It's a bit hard to do in the northern hemisphere. It's mostly in the southern hemisphere. But this is what you would see. This picture on the right. So this is an image, photograph, a long exposure photograph of the galactic center. You see all this dust and gas that accumulates near the center of our galaxy. Right, and so then in the early 1990s, 2 groups, one led by Andrea Ghez at UCLA, and the other by Reinhard Genzel at the Max Planck Institute in Germany, decided to monitor the stars very close to the galactic center. And their goal was to determine whether the stars are orbiting a supermassive black hole. So there were indications before they began their program that the galactic center might have such a black hole, but it was really inconclusive. And so they really thought the best way to do this was by looking at the stars and seeing how they move. And so they used 2 different sets of telescopes. So the Ghez group used the Keck telescopes in Hawaii, and the Genzel group used the very large telescopes in Chile. And these are both 10-meter class telescopes, meaning their mirrors are 10 meters in size. So they're the biggest telescopes we have, the most powerful telescopes we have today. And so these 2 astronomers won this year's Nobel Prize, or half of the prize in physics. Right, and so the idea of the research program is the following. So if you wanted to measure the mass of our sun, you can look at the motion of our planets, the orbits of our planets. And the closer our planet is to the sun, the faster it's going to orbit. And the further away it is, the slower it's going to orbit. And by measuring those motions, you can say, okay, the mass of the sun is, 2 × 10⁻³ grams. And so the astronomers had the same idea. Let's look at the motions of stars very close to the center of our galaxy and see if we can infer the presence of some massive compact object, a black hole. And so the idea is simple enough. The problem is getting precise measurements of the stellar motions. And one of the one of the difficulties in doing that is that the light from these stars, as it goes through the Earth's atmosphere, gets distorted. It basically gets blurred. And you've probably seen this effect before. So if you look at the sun when it's setting, it doesn't look circular anymore. It has this kind of wavy look. And that's because the light from the sun is getting bent by the Earth's atmosphere. You've also probably seen stars twinkle at night, and that's the same effect. The light from these stars is getting bent by the Earth's atmosphere. The Earth's atmosphere is turbulent, and it's sort of moving air, and that creates this distortion that blurs the stars. And so if you want to get a really precise measurement of where a star is and how it's moving, you want to graphics that really completely changed the game. It allowed Ghez and Genzel to measure the positions of stars with much greater accuracy. The idea is a bit complicated, but it's as follows. So imagine you have a star and it's sending light through the atmosphere that gets all distorted and wavy. It comes down into the telescope, and at the back of the telescope, they place what's called a deformable mirror, basically a mirror that its surface can change shape. in just such a way that it compensates for the distortion introduced by the atmosphere. It corrects that distortion and leads to a sharper image. And so I have a movie here from the UCLA group that illustrates the idea. So at the start of the video, it's going to loop through. At the start of the video, this adaptive optics is turned off, and you have these stars, but they all look pretty blurry. And then it turns on, and suddenly things come into focus, and it becomes much sharper. And as you might imagine, when you have this sharper image, it's much easier to follow the motions of the stars and detect each one individually. And so that's just what they did. And so here's a picture, an image of the center of our galaxy as it looked in 1995. And so the scale here, to sort of give you a sense, is about a few thousand times the distance between the Earth and the Sun, from sort of end to end in this picture. And so this is where all the stars were in 1995. And what these two groups did, and I'm just showing the data from the UCLA group, but the Gensel group did basically very similar measurements. What they did is every few weeks, every couple of months, they went back and looked again at the galactic center, and this is what they saw. And so in the top right, you see the years going by. So starting from 1995, we're now at 2005. And they've continued to do this. It's going to go all the way to 2020. And so what you see is these stars are all moving. The stars that are far away from the center of this image are moving relatively slowly. The ones that are close to the center are moving much faster. And some of them go through nearly full orbits. And one of them, this one right here, very close to the center, goes through a complete orbit. It actually has gone through 1.5 complete orbits in the 25 years that these groups have been following these stars. And so this is exactly the data they wanted to see. They wanted to measure these motions and see if they tell you what these objects are orbiting. And so this is just what sort of a 2D projection of the sky. They actually have the 3D motion of these stars. And so let me play another movie that actually shows the motion of the stars in 3-dimensional space. And so the way they can get 3D images or 3D motions is they have those 2D motions in the sky from just the proper motions, angular motions, but then they also have measurements of the velocities of the stars, whether they're moving towards Earth or away from Earth. They can do that by looking for spectral lines of the stars, and when a star is moving towards us, the spectral line is shifted to the bluer end of the spectrum, and when it's moving away, it's shifted to the redder end of the spectrum. And so that gives a motion in the perpendicular direction, and we can reconstruct then the full 3-dimensional orbits of each of these stars. And so this is real data. This is this is not an artist impression or something. This is real data from all the stars that these groups have been following. And so you sort of get this kind of beehive of stars buzzing around this black hole at the center of our galaxy, and then the further away they are, the slower they move. And so there's one star in particular that's been really useful for these kind of measurements. That star goes by the name S2 if you talk to the Gensel group in Germany. The group in UCLA, Andrea Gez's group, calls it SO2, but it's the same star. And what makes the star special is that it has a very short orbital period of only 16 years, which means that in the time that they've been monitoring it, it's gone around about 1.5 times. And what's more, it's on a very eccentric orbit, meaning it has this very sort of long ellipsoidal shape. So most of the planets in our solar system are in very circular orbits, but SO2 is on a very eccentric orbit. And that means that it passes very close to the black hole. It passes about 120 Earth-Sun distances from the black hole, in 17 light hours. And when it gets that close, its velocity gets higher and higher. And at its maximum, it reaches a speed of about 3% the speed of light. which, if you think about it, is really remarkable, because this is a object that's the mass of our sun, actually a little bit more massive than our sun, and it's moving at 3% of the speed of light. So it's just an incredible amount of kinetic energy. And because the star gets so close to this black hole, it feels this really extreme gravity. And astronomers use it to test our understanding of gravity and test general relativity. So, the Newtonian predictions are not enough to explain the observations. We really need, Einstein's general relativity to explain it. And it's a way of testing our understanding of gravity in a regime that's never been tested before. And so let me just say a little bit about what these measurements have shown. So they've shown that these stars are all orbiting the same object. That object has a mass of 4 million solar masses, 4 million times the mass of our sun. If you want the precise measurement, it's 3.96 plus or minus 0.05 million solar masses. That's just an indication of how precise these measurements really are. They can measure the mass of this black hole, which is 26,000 light years away, to percent accuracy. And for a black hole of this mass, the event horizon, the sort of point of no return, is about 7 million miles away from the center of the black hole. So if you get within 7 million miles of the black hole, you're done. You're not getting out of that black hole. Another sort of interesting length scale is something that's referred to as the sphere of influence. So how far out from the black hole can you be and still feel its gravity, still feel its dynamical influence, as opposed to the mass from the rest of the galaxy? And that's about a few light years. So as long as stars within a few light years, it feels the effects of the black hole. And so just for comparison, we're 26,000 light years away. So we're so far away from the black hole that we don't have to worry about it hurting us or affecting us in any real way, other than allowing us to make really cool measurements and see that it's there. And the other thing to say is, one of the things that astronomers have been really excited about is testing general relativity. And so far, it's passed with flying colors. And the hope is that we'll be able to continue testing it with ever greater precision, and seeing if maybe there's some shortcomings that suggest there's a deeper theory of gravity that we need. I'll just briefly mention that there's other ways of inferring that there's a black hole located at the center of our galaxy. So in addition to monitoring the galactic center in infrared radiation, which is what the Keck and very large telescopes view in, astronomers also look in different wavelengths. They look in radio, they look in X-ray, and what they find is that once in a while, the black hole suddenly gets brighter, or the region around the black hole suddenly gets brighter. So for the most part, the black hole and the region right around it is pretty dim, but every so often it flares. And so you can sort of see that in this in these two images on the top right here. So the one on the left side shows the location of the black hole. So there's the star S2 that we talked about that has this really short period orbit. And then right near it is the location of the black hole. And at this t=0, there's nothing there. There's no infrared light. But then you look again 39 minutes later, and suddenly there's a signature. There's light coming out from that location. And so what we think is happening is there is some material near the black hole, and every once in a while, a clump of matter falls into the black hole. It heats up as it falls in and emits light, and that's what we're seeing as a flare. There's also this kind of neat gas cloud called G2 that astronomers were following for some time, starting in 2004, and they're watching its motion, and surprisingly, it just kept going closer and closer to the black hole, and actually basically spun around it, got ripped apart, and portions of it fell into the black hole. And actually, a couple of years after it went through this closest approach, we're now seeing a brightening of the black hole that some have suggested might be the brightening due to this accreted matter. It's not exactly clear why it's suddenly brightening a bit, but that's one of the ideas. And so there are these other indications beyond just these stellar orbits that there really is this massive black hole at our galactic center. And so let me just end with a little bit about what future observations might show. And so over the next decade or so, a new class of telescopes are going to be coming online. So what are called 30-meter class telescopes. So the current telescopes, the biggest ones we have diameters, have mirrors of diameter 10 meters. These new ones are going to have diameters of 30 meters. And what that means is they're going to be able to detect fainter stars at the galactic center and see them in all the stars with higher angular resolution. They're going to be able to pinpoint exactly where the stars are and how they're moving with greater accuracy than we can do today. And so let me play a movie illustrating, the difference between what we can do today and what we'll be able to do with one of these 30-meter telescopes. And I'll just mention that there's 3 different 30 to 40-meter telescopes that are being built today that should, be operating over the next 5 to 10 years. And so this movie first shows what the Galactic Center looks like with a 10-meter telescope today, and now it's going to show what it should look like once we have 30-meter telescopes. And you see so many more stars. You can resolve their motions with so much greater accuracy, which means we can look for more subtle effects in their motions. So we can look for more subtle general relativistic effects than are detectable today. We might be able to detect the spin of the black hole, which is something that astronomers and physicists are very interested in detecting. And it's possible that the black hole, the supermassive black hole at our galactic center, has accumulated matter around it. And one of the, some of the theories predict that it should accumulate a cluster of small black holes that are a few times the mass of our sun, so much smaller than the supermassive black hole, much less than 4 million solar masses. And this cluster can affect the orbits in small but interesting ways. And so it'd be interesting to see if that's really there. Even more interesting, I think, would be if we could detect what's called dark matter. So in cosmology, you show that the observations require a large component of the universe to be made out of something we call dark matter. We don't have any idea what it actually is. It's not the protons and neutrons and electrons that we're all made out of. It's something mysterious and exotic. And there's predictions, there's theories that suggest that this dark matter should accumulate right near the supermassive black hole in galactic centers. And so if it's really there and there's enough of it, we might be able to detect it with these orbits that we would see through these 30-meter telescopes. So I think this field has been exciting for 2 or 3 decades already, and it's very as a demonstration of that, this Nobel Prize is an illustration of how exciting this field has been, and I think it's going to continue to be very exciting once these new telescopes become operational. So I'll stop there. Thank you.
Okay, that is fantastic. We have had a lot of wonderful questions. Again, I'm going to try to save most of them for the end. I do have a couple I want to ask you real quick, Nevin, before we move on. One is actually from the beginning of your talk where you're talking about like the dust in space and the Milky Way and all that. Is that dust the same thing that we consider dust in our home that's like collects on our desk and everything?
More or less, yeah. I mean, it's not made out of the same material necessarily as the dust in our house, but it's particles that are maybe micron in size, and it's it's a mixture of different elements, and it basically blocks starlight from making its way from the galactic center to our eyes. So actually, if you look at the galactic center in optical wavelengths, the wavelengths that our eyes use, basically only one in about 1 billion photons, 1 in 1 billion, make its way through all that dust. So the reason astronomers like Andrea Ghez and Reinhard Genzel look in the infrared is because in the infrared, the dust only blocks about 1 in 10 photons. And so it's much brighter in the infrared than in the optical.
Awesome. Okay, and then one other question is, how do you measure the distance from the black hole? So you have multiple things where you're like, this is 20,000 Earth-Sun distances, but the question specifically because the black hole warps your space, right? And so how are you still able to measure that? Is it the same length as like what we consider still?
Just about. So the warping of space is real, but it only is significant very close to the black hole, near the event horizon. So there is a small correction, within a few Schwarzschild radii, event horizons, distances near the black hole. But once you get beyond that, as Mike was sort of alluding to, space becomes flat, it becomes very nearly Euclidean, and that warping becomes small. And so we can't measure the distance so precisely that that correction is significant. We measure the distance to percent accuracy, but we would need to measure it much, much more precisely to see the distortion of space-time right near the black hole.
Okay, awesome. We will cover the rest of the questions after Yvette's talk. So if you don't mind, Yvette, if you'll share your screen, and also don't forget to unmute.
All righty. All right, let's see here.
All right, we're perfect.
All right. Hi, everybody. Welcome to the last talk of the DFW TAP Talks. I'm a radio astronomer here, and I'm going to tell you guys about what happens if you're not just a star orbiting a black hole near a star that gets too close to a black hole, because this is a bit about my research, and tell you a bit more about some recent stuff going on in black hole research. So to start off with, this is, if you get out of the city, what the night sky looks like. These are stars, right? And this is the Milky Way here. And this is what you see if you're just looking out with your eyes on a very clear night. What I'm interested in, though, is I'm a radio astronomer. I study a very different part of that electromagnetic spectrum, and radio waves are very far away from optical light. And if you had radio eyes and looked up at the night sky, it would look very different from this. What you would see would, in fact, be a picture like this. So what we're seeing here is you can see some of these bigger features here that look like bigger blobs and stuff. Those are probably remnants from supernovae, so stars that exploded thousands and thousands of years ago. But then you also have these little dots, these individual dots, and pretty much all of these dots are not actually stars like what you see in the optical with your eyes. These are, in fact, supermassive black holes millions of light years away from us. So these are, a lot of them are those quasars, for example, that we heard about in the first talk. Some of them are also called active galactic nuclei. So as in the second talk, if you have some gas falling onto a black hole, it's going to give off emission. And that's actually the majority of what we see when we look out in the sky with radio eyes. There's a lot of things we can do in radio astronomy to observe these dots and, figure out what we want to see with them. One that got a lot of press recently was the Event Horizon Telescope. And the Event Horizon Telescope was basically a telescope where we wanted to get the first picture of a black hole. So you can see a lot of effects of them. We can see things, stars going around them. We can see jets shooting out from them, all these different things. But an actual picture of what it looks like where the black hole is. And basically the way we can do this is because obviously that's a very, very tiny thing in the sky to be able to get measurements of. The Event Horizon Telescope, basically the idea was you can link in radio astronomy radio telescopes together to it's called interferometry, to basically make a image where you get the resolution that's effectively the size of the Earth for the size of your dish. So if we link together the South Pole telescope with the Chile telescope with the Mexico, Arizona, you get the idea, basically everything you can see, you will effectively get a telescope the size of the planet Earth. And then you can get some really, really precise pictures that come out of that. It's really hard to do. This is why, this was a really big deal. But it turns out if you do the calculation out, you need a very supermassive black hole to be able to see it, because, you can't just do this with a little black hole that's only the size of a star from Earth. There's two black holes you could do this with conceivably with just using the size of Earth. The first is the supermassive black hole in the center of our Milky Way. The other one is one called M87 star. For various reasons, that's an easier data set to do this with. And then about 2 years ago, we got this beautiful picture, which is the first ever picture of what a black hole actually looks like. This was very exciting. This came out spring of 2019. You probably saw it everywhere in the news media. I think this is probably going to get the Nobel Prize. You know, you guys in a couple years will have to do another talk where you invite an EHT astronomer, because they're definitely going to win, in my opinion, at some point about this. But the cool thing about this as well is we got this image. It was incredibly hard. You know, dozens or hundreds of radio astronomers worked to get this image. And it actually really looks a lot like what the theorists, you know, like what Roger Penrose and these people told us many decades before. And this is, you know, the experiment proving that this is what we're seeing. So what we are seeing here is, first of all, this is a ginormous black hole. This is definitely the biggest one, so 53 million light years away, but it's billions of times more massive than the sun. It's about 1,000 times more massive than the one in the center of our Milky Way. So even though that one's a lot closer, this one is so much bigger, you can actually do an image with it. And so for scale, if you're looking at the center here, this would be the orbit of Pluto in our own solar system, to give you an idea of the sheer scale. This is the event horizon we were talking about earlier. So basically that the light can no longer escape. And this is called the photon sphere. So where you're getting the bending of light around this black hole is what you're seeing here in this galaxy 53 million light years away. The other cool thing, though, about M87, which is worth pointing out, is we were talking about these jets earlier. This is if you took an optical telescope and looked at M87. Turns out this black hole that we have a picture of, you actually have this jet shooting out. It's about 5,000 light years long. We think the material goes even further, and it's relativistic speed. So going at, you know, almost the speed of light, basically this black hole shooting out this material. Should also be emphasized, we really don't understand the physics of what goes on to make black holes shoot out these jets. We just know they exist in the universe. So there's, you know, there's still a lot of mysteries about black hole physics and stuff. Also, my favorite random little trivia fact about this. So you see one jet here, you don't see another jet here. We think there is actually another jet probably shooting out of M87. It's just because of weird relativistic effects, you don't see it. It's called the beaming effect. So anyway, that's just a cool little thing, I always thought. But yeah, so we see a lot of things. And then the next question, of course, is, okay, we saw that ring of light. What happens, though, if you were to go into that event horizon? So here's a little video. It's looping, so we'll watch it a few times. This is if we have a camera and you were to drop the camera into the black hole. Well, obviously, at the end, you are in the black hole. But when we're starting out, what you're seeing to begin with, you're seeing gravitational lensing as you're getting closer and closer, as your camera is falling inward. You're seeing actually everything is turning blue because basically that light is being shifted literally away from you. And then eventually, once you cross that event horizon, all of the universe, basically, you can no longer see it. And as we said earlier, we don't really know what happens when you cross the event horizon. That's really, you know, science fiction has a lot of ideas on what might happen, but really our physics cannot explain what happens there. The other interesting thing to say is, because relativity is very complicated, what somebody who's outside, if you were falling into the black hole, would see something very different and much more horrifying. So this is an example called spaghettification. So basically, if you're going around a black hole and you're falling into it, the gravity that is affecting your feet is very different from the gravity in your upper parts of your body. And you're having the force pulling you down. You're also having shear forces that are pulling you apart. And you would literally be strung out into a string of spaghetti, is why it's called spaghettification. So for you, probably you wouldn't notice this as much because, as I said, the relativistic effects are very different on you. But it's very different if you're outside of that black hole. Now, how do we know this beyond, you know, the theoretical calculation? It turns out, you know, well, people don't really fall into black holes, but stars do. So this is, you know, if we had a star, this is an artist, or this is a simulation of what something like this happens. What happens if a star gets too close to a black hole? And basically, before it even hits that event horizon, the tidal forces are so strong, it will rip that star apart. So half the material of the star roughly will fall into the black hole. The other half will basically spiral out, give off a huge amount of energy and create this shockwave that goes outward. Because this is it's a tidally disrupted star, we call it a tidal disruption event. And this is actually what I study, and what I'm interested in is what happens when these stars get too close to a black hole and get ripped apart, and some falls in, some goes out, and all sorts of different things like that. So my research specifically, I do, as I said, radio astronomy. And what I'm doing is, this is a different network of telescopes linked together in an interferometer, not as big as the entire planet, but it's still, you know, several miles across. It's called the Very Large Array in New Mexico. If you ever saw this great movie called Contact, this is the very same telescope. It just celebrated its 40th anniversary 2 weekends ago, by the way. And I got an observation that day, so that was pretty fun. Yeah, so what we're doing basically with these radio telescopes, as I said, you have all these dots of light further out. Those are not all of them are constant. A lot of them are changing over time. When something like a tidal disruption event happens, it basically you get a huge increase of energy in the surrounding area and a huge increase in brightness. So we can study that in optical, radio, all sorts of different things. And you can study the shock wave for years after the initial event where the star gets tidally disrupted. As that shock wave expands outwards, it interacts with everything surrounding it in that galaxy. And what you're basically going to have is a lot of information how this plays out, as I said, many years after that initial tidal disruption event happens. So one example, this is just an example of what do astronomers actually do. I'm a second-year postdoc, so I got my PhD, and now this is what I'm doing in my research. I study this object called Swift J1644 plus 57. To explain names, Swift is the telescope that discovered it. The telephone directory of numbers there is basically the coordinates of this object in the sky. So on March 28th, 2011, this object was discovered. It was basically, there was no active black hole there. It was not one of those dots in the sky I showed you. And suddenly it was this incredibly bright gamma ray, X-ray, optical, radio, every single part of the electromagnetic spectrum. And people found it was coming from the center of a galaxy 3.5 billion light years away. So incredibly far, much beyond even M87 star or any of those other galaxies. What we figured out happened was there was one of those relativistic jets. As this star got tidally disrupted, it launched one of these relativistic jets. And the crazy thing about this is after a year and a half of this, giant amount of radiation coming out, this jet actually turned off. And this has never been seen before. Nobody predicted that this was going to happen. This has never been nearly studied in detail before that. We haven't actually seen another one since. But it's very cool because normally these jets, they last, thousands or millions even of years. So the idea that you can basically study something that lasts, the length of a postdoc or something is really exciting for people interested in jet physics. And the cool thing is that the radio emission still exists today, and it's going outward, and you can still study this if you have time on the VLA. So to give you an idea what this looks like, on the right here, this is a actual radio image at 6 gigahertz, I believe it was, for the frequency of what you see. On the left here, this is, I do cross stitch, and then if you look at this is basically pixels, and this is literally pixels, so I just like to show off my hobbies, I guess. This is the resolution when you're using the VLA. So as you can see, this is just a point source. This is, 3.5 billion light years away. We cannot get a little picture of this black hole like the EHT did. It's too far away. And, you look at this, basically the colors are an intensity reading is what you're kind of reading out of your pixels here. And the question is, okay, what do you do with this information? The answer is this is at one frequency. We take measurements at multiple frequencies. Then you get basically a change in brightness at each frequency. You're measuring the brightness. Then you can do a lot of very complicated physics about how shockwaves interact and things like that. Shockwave physics is something completely different we don't really have much time for, but you can then pull out of that things like the radius of the shockwave, the energy, the magnetic field it's creating, and even the density of the material it's plowing through, which is pretty amazing. It took me, maybe 6 months to code it up. It's pretty complicated stuff, especially when you have relativistic physics. Just to give you an idea of what exactly radio astronomy researchers do who are interested in space explosions. To kind of show you, though, like beyond that initial, what happens when you fall into the black hole, we actually can use these TDEs to then study even the host galaxies that they occur in, which is a completely new avenue that has not really existed until, as I said, 2011. That really was the first well-studied TDE like this in radio. So I have a plot here, but I'm just going to explain it really quickly. This is radius in terms of distance from the center of the black hole. This is density. We're measuring the number of atoms in a square centimeter. So this would be, if you have one atom, 10 atoms, 100 atoms. So not very dense material at all. Literally, space is not a perfect vacuum. You'll sometimes get a single atom. And what we're basically saying is, okay, so if you're, say, studying the density at the center of the Milky Way, it's going to be much more dense than the density at the center of that black hole we have a picture of, M87. These are some other TDEs. You can kind of study the distance and what kind of densities they have. This, because this is the longest studied tidal disruption event, you can see we're probing a lot of densities. We're going out. This is what I did. This is, a year of my postdoc, roughly. But paper's getting submitted once my boss finishes reading it, guys. It's really science. This is what it looks like. So that's really kind of, what are TDEs and everything like that, and what the actual research in them looks like a little bit. But just to wrap up here, so black holes are obviously very fascinating. They're very popular. They're Nobel Prize winning in multiple ways. There's a lot that we definitely do know about them, enough to get those Nobel Prizes, but there's also a lot we really don't know about them yet. And you really need to always have new ways to sort of probe the area around a black hole. It's such extreme physics. You can't just have a little black hole in your laboratory on Earth. You really have to go out into space and use the universe as your laboratory. So as I said, for example, spaghettification, if you want to study that, you have to find a star that's going to get ripped apart by the black hole, things like that. TDEs are still really new. As I said, it's maybe only about a decade that this field has really come about. And we're really studying a new population of these black holes that haven't really been studied before. And there's always new things you discover when you get a new population out there in the universe. So thanks very much.
That was wonderful. So this has created a lot of conversation, and there's a few things, we'll start with the simple one of how do the names of these different celestial objects get chosen?
That is a great question. First, there's an organization called the International Astronomical Union. You might know them as the people who said Pluto's not a planet, but they also do other things. And one of those things is they designate how do you name things. Like there's committees, guys. It's weird. This is what old men do with their spare time. In the case of these, so M87, there was a guy called Messier in the 1700s, I want to say. And whenever he found a fuzzy thing in the sky that was not a comet, because he was interested in comets, he put them on a Messier list. So this was the 87th object that Messier discovered. As I said, this is the observatory that discovered it and the coordinates. The Assassin is it's a observatory. They're basically imaging they're imaging the entire night sky, looking for transients, so things that change in the sky. And then they have their own designation. So 14 is the year, LI, because that's they start with A, B, C. Eventually you did double A, B, AC, And this is another one that it's an observatory with the coordinates. So this is just for these TDEs. It's very, confusing and not very intuitive.
It's not as fun as spaghettification, that's for sure.
Yeah, I think a journalist actually made up that name. We're not, obviously, we're throwing numbers on things. We're not going to make up a cool word like that. So.
All right, so I have one more question that's specifically to you, and then we'll do a whole panel discussion. And the question is it possible to be half inside the black hole, half outside? And then what would that look like if you were half and half?
I'm pretty sure you'd be dead before. So there is something, to be fair, called Hawking radiation, for example. So Stephen Hawking, who I was saying earlier today, I think he might have won the Nobel Prize had he still been alive in this year, but he, of course, was not. So he was saying, for example, what happens because you can have a particle-antiparticle pop up in space, and what if that happens exactly at the event horizon? So one particle falls into the black hole, the other one goes outward. And that's basically Hawking radiation is what it's called. So there are some weird examples like that, but for most normal matter, it just gets torn apart. And so, as I said, some of that matter can get flung out and some of it goes in to the black hole, but you're going to get very ripped apart and very dead pretty quickly.
Okay, so no one should go hopping into black holes anytime soon.
Yeah, guys, there's no air in space. It's not a good place, so don't do it.
If you want to close your PowerPoint so everyone can see all of our beautiful faces real quick. So I'm going to ask questions. Y'all can kind of choose. Y'all can talk together and decide what order y'all want to answer them. So one of the things that has had a lot of questions are you'll keep talking about center of the universe or this coordinate or over this part of the sky. And so how do y'all choose the coordinates of the sky? What is your central origin? I can hand this off to Weinberg. Nevin, if you want to answer that one.
Sure. I'm a theorist, so maybe it's better to hand it off to an observer.
I would gladly give it to an observer.
This is another one, like the IAU is, by the way, can I just show up? I'm drinking a beer called Cosmic Distortion, which I saved just for you guys. So yeah, it's a Massachusetts beer. But anyway, so we have a coordinate grid in the sky. It's kind of like if you have longitude, latitude on Earth and you project it outward. It's called right ascension and declination. And so this is basically it's like, if you have declination, that's easier to explain. It's literally 0 if you were to project out of the equator, 90 degrees if you project out of the poles. So that one makes more sense. Right ascension refers to like what is above you, because it's a 24-hour thing because the sky moves. So basically everything in the sky has coordinates that are right ascension, declination. Every astronomer can look these up, and then you can go slew your telescope there.
So how do y'all decide what is the center of the universe? Like, how is that measured? There's a lot of questions asking about that. He wants to grab that one. I feel like all three of you be aimed for. So.
You want to go for it, Nevin? Or
I could try. So there is no center of the universe. The universe is homogeneous and isotropic, meaning it's the same in every direction. On a sort of a cosmological scale. So of course, it's not the same in every direction as you walk on Earth, right? That's how you know where you're going. And it's not the same in every direction within our galaxy. But if you sort of zoom out on these really big scales, there's no preferential location in the universe. And so there's no place you can point to that says that's the center of it. And then it gets a little bit more subtle when you start thinking about the geometry of the universe, and it's sort of in a sort of general relativity kind of way of thinking about it. But a common way of sort of explaining it is if you imagine you're on the surface of a ball, let's say like a basketball, and you're all walking around this surface of this basketball. There's no location on that surface where you can say this is the center of that surface. And so that's kind of the same idea. There's no center of our universe. All locations are sort of equally legitimate.
So what about your galactic center then? So that's like the big thing about the Nobel Prize, right? Because that's the center of our galaxy.
Yes, so you could define a center of our galaxy for sure, right? So the galaxy is this kind of spiral shape with a sort of thin disk, almost like a frisbee, but with spiral arms. And for something like that, yeah, you can define a center. But on the sort of universal, on a scale of the universe, there's no center. But on the scale of the galaxy, there definitely is.
Okay. I'm going to ask a couple of things that were a little more specific to each of y'all's talks. So this one was specifically for Michael, Dr. Kesden. How much did John Mitchell's work influence the more contemporary Einstein and newer black hole theorist?
That's a great question. I think not as much as you would think. Because this was very purely theoretical. He was just kind of recognized based on Isaac Newton's theory of gravity that you could have these dark stars, these objects whose escape velocity was greater than the speed of light. But it was just conjecture. It was theory. There was no observations to suggest such things could be real. And then Albert Einstein, who really came up with the theory of general relativity, which is the theory that predicts our modern interpretation of black holes. And back in 1915, when he came up with that theory, there was also long before we had observational evidence for black holes. So he was motivated by different things. He was motivated by, theoretically, that the speed of light, Maxwell's equations of electromagnetism told us in the 19th century that all light, radio waves that Yvette studies, all travel at this speed. But normally when we think of a speed is with respect to what? So the idea that, when you're driving on the freeway and I'm driving 60 miles an hour, you mean with respect to the road. But this speed just popped out of these equations. There was no reference to anything. People assumed there was this ether that filled everything, and it was the speed with respect to this ether. But yet they did all these experiments. They couldn't find any ether. And so Einstein really reinterpreted space and time as a unified phenomenon so that you could have the conservation of the speed of light in every reference frame. And there was also some observational problems with the motion of Mercury around the sun, the bending of light by the sun, that motivated general relativity. So really it went the other way around. General relativity came first for other reasons, and then once you had the equations of general relativity, then Schwarzschild and Kerr found these black hole solutions that kind of captured the essence of John Mitchell's 18th century theory. And then then it was decades later till though they actually saw them observationally in the 60s.
Awesome, thank you so much. So next one, Dr. Weinberg, I think I forgot to ask this one earlier of you. So you had your adaptive optics that made it so your stars stopped being quite so blurry. The question is, why were they blurry in the first place?
Yeah, so it's because of turbulence in the Earth's atmosphere. The same turbulence you feel when you fly in an airplane sometimes, right? That makes the airplane sort of bounce up and down. It's basically motion of the Earth's of the atmosphere, and when starlight passes through that atmosphere and you have these motions, the light is getting bent in a time-dependent way. So it's getting bent a little bit in this direction at one moment, and then a few seconds later it's being bent in another direction. And so then the net effect when you look at these stars is they're not at a very well-defined position. They're sort of moving around a little bit. It's not something we can see with our eyes. We see the twinkle, which is actually a result of that effect. But when you're trying to, when you're using these 10-meter size telescopes and trying to measure things with incredible precision, then it becomes a significant effect and a limitation. And so these telescopes and this adaptive optics allows you to eliminate that distortion and see where the positions of the stars, almost as if the Earth has no atmosphere and you're looking at it as if you're on the moon and the moon has no atmosphere and you can see the stars without any of this distortion. So it basically, in a way, eliminates the atmosphere.
Awesome. That's actually much cooler than I thought. I thought you were going to just say, well, there's more dirt in the air. Okay, and then another question. This one is for Yvette. How do y'all decide who gets to use the big fancy telescopes? So are there ever conflicts of different people needing them at different times, of where they get to point, etc.?
Yeah, so that is a great question because, so these telescopes are all very competitive for the time. Like any picture you've seen there's maybe, 10 times more people who want to use it than there's like literally hours that we can use these telescopes. Each one's a little bit different. The VLA that I use the most for my research and I'm the most familiar with it, they have a call for proposals every 6 months. Anybody on Earth, you yourself, if you're watching this on YouTube, you can also apply for VLA time. Like we've had high school students who have successfully gotten VLA time. You need to do a lot of you have to write a proposal. You have to explain in detail what you want to do and stuff. So you probably do want to find somebody who has experience, who will help you do your proposal. But I had a summer undergrad. He found something cool. We put in a VLA proposal for him. So that's the sort of level. Then there's, radio astronomers who are familiar with the science will read all these proposals. They'll rank them. So basically this is a more compelling case than this one. You can do it. So I basically enter a scheduling block and then the observer at the VLA, I don't actually go to the VLA to take my own observations. I download it off the internet, everything else these days. They can basically say, okay, at this time in the sky, this is in my queue. I'm going to pick this one. If you have something like, ooh, I just discovered a new TDE, there's two options. You either say, I estimate based up these very valid reasons, there's going to be this many TDEs I'm going to want to observe. And then you're just going to have your trigger and you can trigger the VLA whenever, you have good reason to, that's pre-approved. Or the other reason is if you find something you're like, ooh, that's really important and I need time. There's always a few percent at any telescope on Earth called director's discretionary time. And you can apply, but that's very competitive usually compared to the normal time. So if we had another, brand new relativistic jet and we're like, ooh, we really need to look at that tomorrow, then they can do that for you, but in exceptional circumstances. But yeah, it's complicated. It's open, but the VLA is the National Radio Astronomy Observatory. As I said, anybody on Earth can use that one. That's also because there's telescopes in Australia that I've used. I want to be able to go use those. So that's why it's an international thing. It's open skies for those national facilities.
Cool. Okay. So now we're going to have a bunch of questions about black holes specifically, which I think makes sense because we are covering black holes. So one thing is asking about the shape of black holes. Are they always round? Can they have different shapes? How does that affect the event horizon? I feel like this is probably a Michael question, but if any of you feel like it should be yours, grab it.
I'll take a stab on that. It's a very good question, and it's a very deep question. Because the very concept of shape, Nevin and I both mentioned this idea of curved space and Euclidean geometry. So the shape itself is kind of a function of how geometry works. Like, for example, a triangle. We'd all say, oh, what a triangle's a shape. Oh, it's got 3 sides, and there's the sum of the angles in a triangle is 180 degrees. But that's in flat space. But when space is curved, you could actually draw the analogs of straight lines and get the angles depending on whether there was positive or negative curvature, either less than or greater than 180 degrees. So when you say, what is the shape of something, geometry is built into that. So we use different coordinate systems to describe what's going on near a black hole. And in that choice of coordinate systems, certain surfaces could have different shapes. But it's a highly non-trivial, deep question to actually talk about the shape. That being said, I did mention that there were 2 kinds of black holes: the Schwarzschild black holes discovered by Carl Schwarzschild in 1918, and these spinning Kerr black holes discovered by Roy Kerr discovered mathematically by Roy Kerr in 1963. The Schwarzschild black holes, if they're truly spherically symmetric, and so the shape of them are spheres, but that's assuming that it has exactly 0 spin, which is almost impossible just by sheer chance that every single atom that collapsed into that black hole had precisely 0 angular momentum is very unlikely. So in reality, all black holes are spinning. So some may have big spins or small spins, but they have some spins. And then in that case, there can be different regions that can be, since it's axisymmetric, they would be spheroidal. Like the ergosphere, the region where you're kind of forced to rotate around with the black hole, if it a standard coordinate system, would be a spheroidal shape. And the more highly spinning it is, the more kind of compressed, the less spherical that ergosphere is. I don't know how satisfying an answer that was. So
the person who asked that question, if you want more clarification, you're welcome to put it in the chat and we can ask that. But otherwise, I think it's good for now, and we can move on to the next one. The next one is if we have microscopic black holes. So y'all keep showing all these giant ones. If we have the microscopic, if somehow they are found or detected, what would that mean about space-time?
I don't want to hog the line. I could either take that one or pitch it off.
Mike, I think you have a paper on.
I do have a paper on that. That's a great question, and actually it ties in. So Yvette was mentioning that if Stephen Hawking was still with us, he may well have received the Nobel Prize this year. And she mentioned Hawking radiation, which is one of the many phenomena that he helped develop theoretically. So tiny black holes. So there's the theory of black holes. The mass is just a number, and so it could be arbitrarily tiny or arbitrarily big. But this Hawking radiation is much more powerful comparatively for smaller black holes. So ultimately, if the black holes were really, really tiny, they would be putting out a lot of gamma radiation, which we could see. And if they could even explode if they evaporated and went away, and we definitely see that explosion. So first of all, people have looked for these things. We haven't seen any of the explosions yet. We haven't seen a gamma ray background from these tiny Hawking radiating black holes. So that means their masses, if they're out there, the black holes, their masses have to be more than about 10 to the 17 grams, which would be like a mountain or something. If such things formed in the early universe, it would be telling us amazing things about, we've all heard of the Big Bang, that the universe is expanding today and was much hotter and denser in the past. So if we ever found such things, it would be telling us something very revealing about when the universe was less than a fraction of a second old, and the fluctuations in that very early universe. They are still kind of dark matter candidates. The dark matter that Nevin mentioned we know there's this non-baryonic matter out there. It could be in the form of these tiny black holes. There's still ranges that are allowed. And the paper that Nevin was mentioning, which I almost hesitate to bring up, I kind of wrote a paper that it's almost the opposite problem of Yvette's problem. Yvette said, I've got this really big supermassive black hole, and then if a star gets too close, it gets ripped apart, it gets spaghettified. I was like, let's flip that on its head. If we have a normal star like our sun, and then we have a very, very tiny black hole, a super micro black hole, what would happen? And actually, these black holes are so compact, they would sail right through the sun. It'd be like one of those old cartoons where you run through the wall and you leave a cutout when you pass through. And so it would be like it would carve a hole out through the sun, which would be very tiny if it was a very micro black hole, like an atom-sized hole in the sun. But it would squeeze at the same tidal forces that rip apart a star. If that tiny black hole passed through the sun, it would cause it to squeeze and slosh around. And so we can use the sun as a giant detector to rule out some of these micro black holes. But they'd still be quite rare. We'd have to get lucky to see one.
That's actually really exciting. I
would just add, I mean, the smallest black holes that we know of are, a few solar masses. A few times the mass of our sun. And we know those from these LIGO observations that Mike mentioned. So we see these, objects merging, in some cases, two neutron stars, and we think they left behind a black hole that's, maybe 3 or 4 solar masses. We don't have any proof that such lighter black holes would exist, but there's no theoretical reason why they couldn't, right? It's basically just a matter of putting enough mass in a small enough volume that the escape velocity from the surface would be larger than the speed of light, and then you have a black hole. So that's why sort of theorists kind of wonder and think about these things, not because we have observational proof, but because we have no proof to the contrary that they can't exist.
Awesome. Okay. So we're getting several questions on white holes. There was one earlier too I'm trying to find, but could you all comment about white holes? What are they and why are people interested in them? I don't know who to give this one to because I know you all work in black holes.
I don't want to hog the spotlight. I'm not an expert in such things. I could stab it unless somebody else wants to take it. I could try to answer that question.
I'll make sure the next question goes to someone else. But if you'll grab this one, Michael, please.
So white holes, that's a great question. It's kind of like the time reverse of a black hole. So we said that the defining quality of a black hole is something that has an event horizon. So it's this boundary, and that inside that boundary, everything is invariably directed inwards towards the singularity. Whereas a white hole, since it's the time reverse there, whereas nothing can get out of a black hole, nothing can get into a white hole. So essentially all of the, even if you kind of shined a laser beam at the white hole, trying to get those light photons into the white hole, they wouldn't make it in. So it's almost problematic. I mentioned that Roger Penrose is famous for this thing called the cosmic censorship conjecture, that you can't have naked singularities. So there's these singularities where space-time curvature gets infinite and it's very wonky, but because they're not naked, they're clothed by their event horizons, you can't see them. Nothing can get out. It's kind of like if a tree falls in the forest and there's no one there to hear it, it doesn't make a sound. If there's a singularity inside the event horizon, but no light, no one can see it, is it even there in the first place at all? Whereas white holes, everything is forced to come out. So there are these singularities at the center of the white holes, but they don't have any horizons, they have the opposite horizon, so everything is thrown out. So our theory breaks down. We get a Nobel Prize if we could find a white hole, but we don't know what infinity looks like, so we don't even know what the signature would be. And so it's kind of a mathematical construct that almost by design is impossible for us to know what it looks like. And I don't know who, I mean, it's very hard. I think it hasn't had a lot of great interest in the scientific community just because we have no idea, how to interpret what such a thing would look like. And so there's much, very hard to look for something you don't know what it looks like.
So if I can add on to that real quick.
Yes.
So the first thing is a really bad physics joke, which is if you're a theorist and, if you're an experimentalist and you get 10% of your stuff wrong, you're a terrible experimentalist. If you're a theorist and you only get 10% wrong, you're a terrible theorist. And the other reason you should have like a lot of ideas that they're not quite there. So, we're talking about things like white holes. There's no experimental evidence out there, and I'm a very big experimentalist, so I just wanted to emphasize that. There's also, as we said, there's a lot of physics we just don't understand about black holes. So I don't think anybody thinks, for example, that things are literally infinitely dense inside of a black hole. It's just that's what our current physics tells you happens. You're approaching infinity. So the idea like, okay, a white hole can also come out of that in the reverse, that doesn't mean that it must happen. It just means that our physics, eventually Einstein could not explain what happened when things were infinite, like getting toward infinite mass. So.
Okay, that actually leads directly into this next question. It's going back to Hawking radiation, where you have your matter-antimatter pairs on the event horizon. So the question is, if this is true, that the Hawking radiation is a thing, does this mean that the stuff in the black hole is space itself? And I'm not quite certain what this person meant by space, but Yvette, if you want to try to handle that one.
I don't know the answer. So
that's right. I know that we're literally saying we don't know what's inside of the black hole. So
yeah,
sorry on that question. I wish we had more information on the inside of a black hole. I kind of expected that to be the answer.
Yeah, unfortunately, there's just once you're inside the event horizon, you just can't know what's going on in there.
So this next question, I think, is very interesting. What are the circumstances where there can be a galaxy formed where there's not a black hole in the center?
Oh, well, that's an interesting one because I think everybody's pretty much concluded any galaxy that's like a galaxy our size, where like an average size galaxy has a supermassive black hole in the center that things orbit around. You can have very small galaxies, so like we have satellite galaxies to our Milky Way. Which are, maybe at maximum a tenth the size of the Milky Way. They don't appear necessarily to have supermassive black holes in the center of them. But yeah, as Michael was saying in his talk, you have these very small black holes, you have these very big ones. You don't really have much in between. So then, do maybe they live in the smaller galaxies or something? There's a lot we don't know about that and like how those supermassive black holes got into the center of these galaxies.
I wanted to chip in just something quickly. One of my favorite questions, I used to pester every observational astronomer I met this question. Maybe I'll even pester Yvette about it. One of the closest satellite galaxies to our own are the Magellanic Clouds. And these things are smaller than the Milky Way, but they're by far not very puny galaxies. They could have a mass of, hundreds of millions or a billion, solar masses. And I asked people, are there supermassive black holes at the center of the Magellanic Clouds? And I get, or what is the upper bound? If that's an experimentalist, you can never rule it. You can never say there's nothing there. You can just say, if it's there, it's got to be smaller than a certain value. And I get a lot of blank stares when I answer that question. And part of that is because, they need an X marks the spot. If the galaxy has a very bright center, then people know, Andrea Ghez and Reinhard Getzel know where to point their fancy telescopes, and they could try to look for stellar motions and see if there's a supermassive black hole there. But some galaxies that, even if they're not that small, just are irregular in shape and just don't really have a clear, well-defined center, you'd have to just randomly search through the whole galaxy to look for a black hole. It'd be very hard to do. So observationally, it's a very interesting question. And then another one, there's this famous thing called the M-sigma relation. There's a relationship between the mass of a supermassive black hole and the velocity dispersion of the bulge component of the galaxy. Like our galaxy, Nevin said, was a spiral galaxy, but it does have a bulge at the center. There are these things called bulgeless spirals, which are things that have spiral disks like the Milky Way, but for some reason having to do with galaxy formation, they don't really have a bulge. And there's M33 is the Triangulum galaxy. It's one of that Messier catalog Yvette was mentioning. It's also a fairly big galaxy, very nearby us. But we have a very tight upper bound, I think, on just a few thousand solar masses, which is very puny for a supermassive black hole. So there are some cases where you can it's kind of in the nature of the galaxy formation. Make a galaxy without making a supermassive black hole. It's rare, but it can happen. Sorry, yeah.
I would just mention there's a flip side to this where we think some galaxies might have two supermassive black holes at their center, because one of our ideas is that how galaxies form and how the universe evolves is through the merger of galaxies. And so if you imagine you have two galaxies, each with their own supermassive black hole, well, then you're going to have two supermassive black holes that are going to eventually make their way to the center. And so I don't think we have any definitive proof of such a galaxy, but there's efforts to look for that. And actually, one of the future gravitational wave detectors that's being considered to be built, one of its goals is to look for gravitational waves from two supermassive black holes that are orbiting each other.
So there is, do you know the Cygnus A? I think it's Cygnus A had the second black hole that showed up recently. Did you hear about this? I'm pretty sure it's Cygnus A. So This is a radio astronomy thing. So Cygnus A is like Sagittarius A star is, the center of the galaxy is the brightest thing we have in the radio sky. Second brightest is this Cygnus A black hole at the center of the galaxy, which is pretty far away. And then a couple, like 2 or 3 years ago, a team at the VLA, actually a father-son astronomer pair, which I always thought was kind of cute. They basically re-imaged this galaxy and they discovered that there's the supermassive black hole. There's now a second really bright thing next to it, which they think is also a supermassive black hole, which was definitely not there in like the 1970s. So that might be a candidate for a second supermassive.
Or it was there, but it wasn't accreting, so it wasn't bright.
Yeah, it was. Well, I mean, it was always there. The question is, we only see it interacting with other things. So that is apparently a pretty good candidate for that. So.
Awesome. Okay, so I think we have one more technical question, and then we still have more questions. But the last technical question is, so we always talk about like your mass is probably getting compressed inside the black hole. What happens with all the charge of electrons, et cetera, that gets sucked in? Do those also get compressed, theoretically? Nevin, does this one go to you now that it's not?
I can try it. Yeah. I mean, so black holes obey what's called this no-hair theorem, where a black hole can be described entirely by its mass, its spin, and its electric charge. And so black holes, at least in principle, could have a charge. So if a black hole just secreted a whole bunch of electrons and not protons, it would become negatively charged. We don't know of any black holes that are charged. We think they're probably almost perfectly neutral because matter tends to be neutral. So it's hard to sort of invoke a scenario where a black hole would only accrete electrons and not positively charged protons and nuclei. So yeah, I think I mean if you accrete matter, it's just going to be electrically neutral and just not show up as a net charge on the black hole. But in principle, that is possible. It is one of the features that a black hole could have. We just don't know of any.
Okay, cool. That actually works really well on that. So the other one, there were questions throughout that kept getting scattered, both beginning, middle, and end. So can we talk about wormholes for a second? Are those related to black holes? Are they real? And do any of y'all know about them?
Wormholes, you said, right?
Wormholes, yep.
I think they're a very good science fiction device because you can't travel faster than the speed of light. But once again, once you get inside that event horizon, because we don't know what can happen, anything can happen. So, but I'm the experimentalist. Maybe these guys have other opinions there.
I think one of the things, again, I'm not an expert on these. I haven't worked on them. I think people showed that if you had a stable wormhole, you would need some kind of, to prevent it from collapsing, you'd need something that has negative energy density, which is something, everything that, Einstein said E equals mc squared, energy is equal to matter. And there can, there can be things that have, antimatter, you may have heard, which has all of our particles have the opposite charge and whatever, but that's still, it has positive mass, positive gravity. So theoretically, temporarily, one might be able to curve space-time in such a way to create something like this wormhole idea, this way that kind of it's a shortcut to go. Two different paths could connect two different events in space-time, and one would be a shortcut. But if it wasn't going to collapse in like the speed of light, crossing the thing, it wouldn't collapse in seconds or something. You'd need some very exotic matter, which is, again, in the realm of science fiction, like Yvette said. I mean, then you could also have these issues. Another thing people talk about is closed time-like loops. Remember, we talked about space-time. If you can curve space and time are the same thing, you could curve time as well. And then you get paradoxes. If you could go, instead of just going forward in time, there's a closed time-like curve, and you could come back around to your past and assassinate your grandfather and whatnot. That also seems problematic. And so once, as exotic, as crazy, all these things are can be connected together. And so once you open the door on one thing, you start opening the door on a lot of other possibilities that really challenge our intuition about how the world works.
Okay, so we're only going to ask a couple more questions because it's getting kind of late, but we are going to have to pull in some dark matter because there's been a couple of questions on that. This is probably Nevin's wheelhouse, but y'all can correct me. So one of the questions that started this is, isn't the observable universe like a donut where we have dark matter at the center and at the outer edges as well? And the follow-up on that question is, does dark matter or dark energy interact with black holes? I'm feeling like this is going to take a couple of minutes. I'm going to be right back. But if y'all go ahead, probably Nevin, this is yours, but please, I'll talk about it.
Yeah, so dark matter, we think, is sort of spread throughout the universe, but tends to so it only interacts gravitationally. And so it tends to pull ordinary matter into it. And so we think that where galaxies are located, the density of dark matter is higher than in regions where galaxies aren't located. So there's regions of the universe where we have voids where there's very little matter, and we think there's probably very little dark matter there too. It's not donut shaped, we don't think. We think that at least in galaxies and clusters of galaxies, the dark matter is probably roughly spherically distributed. It's highest density near the center, and then it falls off, with some scaling, some decrease in density with radius. But it sort of acts just gravitationally. It's mysterious because it doesn't interact in any other way. It doesn't interact with photons. It doesn't interact with electrons. It just everything can kind of pass right through it and just feel its gravitational effects. And so it came up in my talk in the context of the black hole at our galactic center, because one of the predictions, and this is not universally accepted, but one of the predictions is that near these supermassive black holes, you'll get a steep cusp, steep increase in density of dark matter. And if that's really true, then you can see its effects on the stellar orbits. You basically have not just almost like a point mass from the black hole, but you have this distributed mass of dark matter. And as these stars orbit, they see, and if it's on an eccentric orbit, and on its outer part of its orbit, it's going to see more dark matter than on its inner part of its orbit. And so that difference in mass between the inner and outer parts of its orbit can lead to what's called precession. The orbit doesn't close in on itself. It has a kind of like a petal shape, like a flower-shaped petals of a flower. And so there's reasons why people are excited about making these measurements in the galactic center, but for the most part, it's kind of speculative, and we don't have any proof that there should be dark matter there. We just think it might be.
Okay, thank you. I think we actually have time. We might be able to finish up all these questions. So if y'all don't mind, so why are galaxies so spread out from each other? Why don't they all just become a black hole and all scooch in? We've got gravity. Who wants this one? Yvette, do you want this one?
I could try, and then so obviously the Big Bang happened, and then the universe started rapidly expanding from this infinitely dense, hot, small point, right? And basically, as this expansion happened, like the matter kind of expanded with it. And then so that's like the first answer. Why didn't it all just become a giant black hole? Is because the expansion was fast enough that you didn't immediately get a black hole from everything in it. Then basically the matter starts to clump, and there's actually very different distances between galaxies. They're not all like evenly spread out. Like you can actually get like these strings of galaxies. If you look at the large scale structure of the universe is what it's called. So basically galaxies kind of are in these lines. So the matter is somewhat clumped in regions. There are some big voids that are like, you know, millions and millions of light years across where there's no galaxies. Then suddenly you'll get clumps of galaxies. Some galaxies are also, of course, gravitationally bound. So like there's the Andromeda galaxy near us that's going to crash into us someday. But further out, the Virgo galaxy, so M87, which is 57 million light years away, we're actually very long time going toward that Virgo supercluster of galaxies where M87 is 57 million light years away. So there are various clumps and stuff like that in there, but the distances are basically just so much bigger than the mass.
Okay, that's perfect. Thank you.
The only thing I would add to that is also there's just angular momentum. Like if you think about our galaxy, the stars, it's a spiral, but they're all sort of orbiting, and their angular momentum basically prevents them from falling inwards. In the same way that Earth doesn't fall into the sun because it has angular momentum that keeps it in its orbit. So the stars in our galaxy have angular momentum that keep them from all collapsing inwards.
Oh, and it should also be noted, actually, tying into the previous question, because people are always like, oh, is dark matter just a signature from the galaxy rotating and stuff? Actually, it turns out if you don't include dark matter in your simulations of how the universe gets the structure that we see today, it doesn't work. So that is something also to keep in mind. It's not just like the galactic rotation or something like that. So,
that's pretty interesting.
Mm-hmm. But I mean, that's people's entire career who are not on this panel. So that's like a very detailed.
Right. We'll try to have a dark matter talk sometime next year, or dark energy. We'll see what we can end up. But it's not currently on schedule, but we will try to get it. So one of our last questions is, do y'all ever think it's going to be possible that we can know what's inside a black hole, if there's something there?
I hope so. I don't like, I feel like, things we can do within my lifetime. Now that's like another one that's maybe more complicated, but yeah.
I'm pretty cynical about that one. I think there's so, with the Event Horizon Telescope really gave us, and LIGO as well, has given us just spectacular evidence that these event horizons exist, and getting information out of them is going to be, well, not just within our lifetimes, but very hard to do, unless physics is, one could always think, there are still a lot of questions that we don't know the answers to, like Yvette said. General relativity is not our ultimate theory of gravity. So if in the quite distant future, people discover that gravity is really quite different from what we imagine it to be, then the story, everything's off, but not easy to it's not just technologically impossible to get information about outside of these event horizons. It's theoretically impossible. So it's tough. It's very tough.
If you could get the information if you jumped into a black hole, you just couldn't share it with anyone.
So it depends, how passionately committed you are,
Awesome. So there's actually just a follow-up question on the white hole that I think is fantastic from Joel Roberts. So according to Michael's explanation of white holes, could the Big Bang have just been a white hole?
I think some people have said that, theoretically. Yeah.
Is that right?
Yeah,
at the beginning of time.
I'm sure there's been a paper. Yeah.
People say, there was a singularity. So he mentioned singularities, that there's singularities at the centers of both black holes and white holes. And certainly if you rewind, again, as Yvette also made this point, which is a really important point, that infinity is not really a physical thing. It's just mathematically our theories are predicting it. It's a sign that our math is wrong, not a sign that necessarily physically there's an infinity there. So there's singularities. Singularity is just a fancy word for infinities. There's singularities in black holes. And if you say, oh, the universe is expanding and we rewind it into the past, if you rewind it back, 13.7 billion years, you get another singularity at the Big Bang. But two infinities are not necessarily equal. I mean, the white hole is really it's just like a sign flip of a black hole. So it's a stationary it's a vacuum solution that there's nothing there. And it's stationary. It's not, even though particles can orbit the black hole, so things can move around it, the black hole itself mathematically is stationary and fixed in time. Whereas the Big Bang is the opposite of kind of being fixed in time. I mean, the universe is expanding, its density is going down. There are other kinds of horizons associated with the universe. When the universe was very young, different things were out of contact with each other, because if the universe is only 1 billion years old, things that are further, crudely, if things are further than 1 billion light years away, then they can't communicate with each other. Just in the whole age of the universe, information couldn't be exchanged. So that's something they call a particle horizon. So there's other kinds of horizons associated with cosmology, and that it's more complicated than just saying, oh, the Big Bang is a white hole. I mean, there's some similarities, but also vast differences. It's between those concepts.
All right, so I think this last question is going to take a little bit of time because I want each of you to answer it. And the question is, what do you personally think is the next step in black hole research? So I feel like this is one that each of you are going to have an opinion that's probably very, each completely valid. So we're going to go in a circle. We'll go in the order that y'all are on my screen. So Yvette, if you want to say, what do you think is the next step in black hole research? Try to keep it under 4 minutes if you can. I know that's hard.
Okay, well, under 4 minutes. I think sort of the big thing that's happening, unfolding in the next few years is, we said LIGO briefly, is a huge black hole finding machine. Honestly, LIGO has been far more successful at finding black holes than people were initially expecting. Like, it turns out they're... Yeah, it's people thought the neutron star mergers would be the ones that are found more, and it turns out the black hole ones are. There's also supposed to be like black hole neutron star mergers detected, and things like that. So for me, that's like basically because gravitational waves, it's the equivalent, they say, of, if you're seeing the universe for basically all of humanity, now we can also hear the universe. You literally have a new sense. So then we're really opening the window to these events, and astronomers like me, one of the things my group does, because we're just looking for giant space explosions, we get these triggers. I even get them on my phone. You can get an app and download it. When LIGO is on, you will get a trigger alert on your phone that, oh, here's the sky map, where we think it's going to be like sometimes half of the sky, by the way. It's like not a precise science yet by any means, but you can go out then with your telescope and look for these. If you just have a black hole merger, we don't think those really give off electromagnetic radiation, but say neutron star black hole merger, things like that. And basically, they did find the one neutron star merger. They did find an electromagnetic signature from that. And that, we've got a ton of information about, like, where a lot of different elements come from in the universe. A lot of answers got out of that one observation. So I think that's really kind of the direction, like with LIGO and all the things that are going to be discovered, also in connection with electromagnetic stuff and the follow-up that's going to happen there. I think that's really, the population of black holes that we already have is already just very different there, and seeing that go together is going to be really powerful in coming years.
All right, Nevin, how about you?
I'm gonna have to go with LIGO too. It's just been, just in the last 5 years since the first detection of gravitational waves from black holes, it's just been sort of one interesting thing after another with what LIGO is seeing. I can mention the sort of most recent observation that's kind of a mystery, which is that they saw the merger of two black holes. I think one was around 60 solar masses, 6 times the mass of the sun, and the other was about 85. And there's error bars on that. But what was surprising about it is there was this very firm prediction before this observation that they should never see a black hole between about 60 and 100 solar masses, that stars just can't make those kind of black holes. If a star is too massive, then it blows itself up and doesn't leave behind a black hole, and it just wouldn't leave a black hole in that mass range between about 60 and 100. There's some uncertainty there, and so now people are sort of going back to the drawing board and trying to come up with, oh well, actually maybe we really can do this, but it's kind of after the fact, and so it's just kind of one of those things where theorists can make statements and claims and be very confident in themselves, and then observers make a measurement and say, actually you're wrong, and then the theory is saying, oh well. And so it just kind of, I mean, that's just one example, and it's been like that, I think, for the last few years with LIGO. And so I think I'm almost certain there's going to be more surprises like that in the coming years.
That's very exciting. So this is stuff that people can keep on watching and staying tuned for.
Yeah, I mean, and again, well, I'll add my own flavor on it, but again, I'm also going to go with gravitational waves. That's why I put in a few slides, even though it wasn't specifically relevant to the 2020 Nobel Prize. It cannot be overstated the amazing scientific return and continuing scientific return of LIGO and gravitational waves more generally. Electromagnetic radiation comes in a whole range of wavelengths. There's a whole spectrum. The human eyes just see, between 400 and 700 nanometers. And people have been looking at the night sky, the stars, for, since humans existed. But over time, electromagnetic astronomy has expanded into the radio that Yvette works on so hard. But there's also people study the infrared. Remember, we need the infrared to see the center of the galaxy because of all that dust. There's X-ray astronomy. X-rays are also great. They let, X-rays, you can see your bones with X-rays, gamma rays, ultraviolet. So these are all electromagnetic waves, just with a whole range of different wavelengths. It's the same thing with gravitational waves. They also come in a range of wavelengths. And so LIGO is seeing within a particular range between about 10 hertz and 1,000 hertz. But in the near future, we're going to have this thing called LISA, which is a space-based version of LIGO. So instead of having those 4-kilometer tunnels here in Louisiana and Washington State, we're going to have satellites that are 5 million kilometers apart. And so those longer arms gives us sensitivity to much longer wavelength gravitational waves coming from supermassive black holes like those at the Galactic Center. We'll see every supermassive black hole merger in the entire universe when LISA's operating.
Probably more of those than of these little dinky black holes merging, by the way. That's
and that the signal to noise ratios will be thousands. So we'll be able to make precision tests of these horizons even better than LIGO. And also there's the next generation. LIGO is going to wrap up in another 5 years. And then there's these next generation. There's this Einstein telescope in Europe, an underground bigger LIGO, and this Cosmic Explorer in the US. And so we will see every binary black hole merger in the universe, 100,000 a year, and 1 million neutron star mergers a year. So in terms of the data, I mean, we go from a handful of events, now to 100 with LIGO, to 1 million a year of neutron star mergers. So it blows my mind, just the progress of technology. You maybe have heard about, people also use the phrase singularity to refer to artificial intelligence. What happens when computers get smarter than we are and they build even smarter computers, and it kind of the singularity of computers. Now humans have been looking with their eyes for thousands of years and building bigger and bigger telescopes. We will go with gravitational waves from the discovery, the very first source in 2015, to 20 years later in 2035, all the way, the whole horizon, the whole universe. The universe is 14 billion years old. We'll be able to see the black hole mergers 14 billion light years away. And so just that idea that 20 years from birth to everything, it just blows my mind about the level of progress of science and the mysteries that LIGO is going to reveal in those different bands. I could go on and on. I've outrun my 4 minutes, but it is a revolution. Gravitational wave astronomy is a revolution on par with the cosmological revolution over the past 20 years, and I just can't wait for it.
So can I share a very quick anecdote? So about 2 years ago, I went to a conference in Stockholm, and if you ever go there, there's a Nobel Prize museum you can go to, and if you win the Nobel Prize, you get to donate something to the museum. So Peter Higgs of the Higgs boson donated beer, for example, which I'm not sure about, but seems relevant.
That's my kind of guy.
But the LIGO team donated the wafer that was like the detector that made the first gravitational wave detection ever. So someday when we're not all on Zoom and you can go to Stockholm at your leisure, you guys should all go, and that's where it is if you want to see the birth of gravitational wave astronomy. So
that's pretty cool. I didn't even know that museum existed, actually.
It's a pretty interesting place. There's a lot of interesting people who won the Nobel Prize, guys. So.
All right. Well, thank you all so much for giving us talks and answering all the questions. We actually didn't cover all the questions. I apologize. We are running out of time, so I'm going to have to skip a few of them. Thank you to all our viewers who have been watching. If you appreciate what we do, please consider liking and subscribing. It does help us greatly, and all it takes is a couple of clicks on your end. You can also follow us on Facebook, Instagram, and Twitter, as well as our website, dfwtaptalks.com, to see the upcoming talks that we will be continuing to have. And eventually, maybe we'll be back in person. But until then, thank you all for joining us on YouTube Live.
Thanks, everyone.
Bye.